In our previous tutorials, we looked at different techniques to design RF and microwave amplifiers. We started with the unilateral matching technique, which assumes that the input and the output of the transistor are independent of one another. This means that we can devise a matching network for the input and one for the output independently of one another to achieve the desired specifications. We can think of input and output matching networks as gain dials, which allow us to adjust the gain by adjusting the amount of mismatch that is present at input and output ports. These techniques, however, can only be successfully used when the S12 s-parameter of the transistor is negligible. Remember that the S12 gives us an indication of how much interaction there is between the output and the input of the transistor. In our tutorials, we saw that when we use this technique with a transistor, when the S12 is not negligible, we end up having to go through a process which may involve several iterations in order for the right specifications to be achieved. Because of the inaccuracy of this technique, when the S12 is not negligible, we moved on to a different technique called simultaneous conjugate match, which is an exact technique, and it allows us to achieve the maximum small signal gain for our transistor. However, there are two limitations to this technique. Firstly, it can only be applied when the transistor is unconditionally stable. And secondly, input and output matching networks cannot be tuned in order to achieve a different value of gain. There are, however, other techniques that can be used when the S12 is not negligible and that allow us to tune the gain of the amplifier. These are based on operating power gain circles and available power gain circles. In this tutorial, we will be looking at the operating power gain circles technique. In this tutorial, we will not be using nonlinear models for our transistors and working out bias networks and stabilizing networks. We will instead use the measured s-parameters for the transistor of interest. Remember that s-parameters are bias dependent, so the s-parameters that we will be using will be relative to specific bias conditions for our transistor. First of all, let's open a new schematic, and we'll call it Operating Gain Match. And then let's press Ctrl L and pull up an element called S2P block, and then click to place on the schematic. This block allows you to specify the s-parameters that you want to use. However, you have to be careful in that these s-parameters will be relative to one specific frequency and one specific bias level. If we right-click on this element and then select Help, we get some more information on how to use it. You can see that the s-parameters have to be defined as complex numbers in a Cartesian form in this case. So if you had s-parameters in a polar form, you would have to convert them before using them with this particular type of element. Although this appears to be a quick and easy method, I think that there is a much better way to use given s-parameters in a simulation, and that is by using an S2P file. Many manufacturers already give S2P files for their transistors, which are files which contain two-port s-parameters for a particular device at a specific bias level across a range of frequencies. And I'd like to talk a little bit about this type of file before we carry on, and then we will be using one for our design. We can open a new data file by right-clicking on Data Files and selecting New Data File. Then we can give it a name, example S2P, and selecting Touchstone file as the file format, and then Create. This is a very simple text editor which allows you to write the s-parameters in, and then you can save this file and use it for other simulations. The syntax to write these data files is very easy. To insert a comment on the data file, you just put an exclamation mark at the beginning of the line. We can write anything here. We can say example s-parameter file, and then you want to specify the format of your s-parameters. To do so, you need to put a hash at the beginning of the line, and then the first parameter that you have to set is the units of the frequency that you have used to measure your s-parameters. In our case, we will be saying gigahertz, but you could set this to megahertz or kilohertz, for instance. Then you have to specify the type of parameters that this file contains. You can have s-parameters, but you can have also impedance parameters and other types. In our case, it would be s-parameters. So we'll just type S right there. The next parameter that we need to specify is which format you will be putting the s-parameters in. This is one thing that you can't do with the s-parameter block. You can only have them in Cartesian form. Instead here you can then have them in magnitude and angle, for instance, in which case you want to type MA. Then you want to specify your normalizing impedance, and you do that by typing R followed by the value in ohms of the normalizing impedance. In our case we'll say 50. Now we'll go to a new line and we need to write a line which contains our s-parameters. There is a specific order in which the s-parameters should be typed in, and I'm going to insert a comment line to specify this. The first element has to be the frequency for each s-parameter set, and then you have to put in the S11 magnitude, then the S11 angle, the S21 magnitude, and then the S21 angle, then the S12 magnitude and the S12 angle, then the S22 magnitude and the S22 angle. Then you can just type your s-parameters in, but first of all you have to write the frequency to which this s-parameter set corresponds. So for example, if at 1 GHz our S11 was 0.2 and had an angle of 120 degrees, this is what we'd write. Then we'd write the S21, which is say 2.5 with an angle of 40 degrees. Then we can write our S12, 0.02 say with an angle of -30, and then finally the S22, say 0.6 with an angle of 45 degrees. Then we could do the same for a different frequency. So say we have them for 2 GHz, we write 2, and then again we can put the s-parameters in much in the same way. So if you have a set of s-parameters and you want to use them in your simulation, the best thing to do is to write an s-parameter file, and then you'll be able to save this and you'll be able to use it in subsequent simulations, rather than using an S2P block. This also gives you the advantage to define s-parameters at different frequencies all in one place, and also it allows you to specify a different format for the s-parameters. Now let's delete this file, and the other thing that we can do is right click on data files and import a data file. This could be a file that we've already written, or a file that we've obtained from experimental tests, for example from a network analyzer. So we'll just click on import data file, and then we can pick an S2P file, and it will be imported into the simulator. In this case we'll choose the operating gain transistor file. Now you can see that under the data file heading we've got this operating gain transistor block, and if we double click on it then we can see exactly what this file contains. You can see that there is a comment line at the top telling us what the testing conditions were, what the bias conditions were for this particular transistor. Then we have a line which starts with a hash and sets all the parameters that we need to set. We have units of gigahertz, we are looking at s-parameters in magnitude and angle, and we have a normalizing impedance of 50 ohms. And then again we have a comment line which reminds us of the order in which the s-parameters have been written. And then finally we have the s-parameter data. This tells us that the s-parameters were measured at 6 GHz, the S11 is 0.641 in magnitude and -171.3 degrees in angle, the S21 is 2.058 with a 28.5 degrees angle, etc. And then we can effectively use this imported data as a model for our transistors when we're operating at 6 GHz. Now we can go back to our schematic and remove the s-parameter block, and we can drop the s-parameter model for our transistor in the schematic. How do we do that? We just click on the sub icon on the top menu, and then you can see that a pop-up window appears which gives us a list of the sub-circuits available. In this case we've only got one because that's the only one that we have imported. So click on OK and then place it on the schematic. You can see this is a two-port block, so one would be the input of our transistor, two would be the output, and these are the ports that were used to measure the s-parameters. So what we can do is add measurement ports to this schematic by pressing Ctrl P. We'll add one port for the input and then again another one for the output. Then we need to go to project options and set the correct frequency. So in this case our s-parameters were measured at 6 GHz, so 6 will be our frequency. We select single point and then apply, and then OK. You can see what's inside any block just by clicking on the block, and then click on the arrow pointing down on the menu up here. And this will go inside the block and tells you exactly what it contains. Remember that these s-parameters were measured at a specific bias level. They are bias dependent. To go back to the schematic, just click on the arrow pointing up and you're back to where you started. Now, first of all, we'd like to see if our transistor is stable or unstable at the frequency of operation. So we go to Graphs, select New Graph. It'll be a rectangular graph and we'll name it Stability Factors. And then we right-click on the graph, go on to Add a New Measurement, and then under Stability we will select mu1 from the operating gain match schematic, and then click on Apply, and then mu2 and click on Apply, and then OK, and then Simulate. Well, we can see that both the mu2 and mu1 factors are greater than 1, and this means that the transistor is unconditionally stable at 6 GHz. Now let's open another graph, and it will be a tabular graph, and we will call it Gains, and then we'll add a couple of measurements on there. First of all, we'll look at the basic gain of the transistor, which is given by the S21, and we do that by selecting Port Parameters, S-Parameters, S21, and then we'll select Magnitude and dB. Click on Apply, and also, since the transistor is unconditionally stable, simultaneous conjugate match should be possible, and the simulator gives us a measure of what is the maximum gain achievable if the simultaneous conjugate match is applied to the input and output of the transistor. We can find this measurement under Gain and GMax. So GMax gives you the maximum available gain, which tells you what gain you can achieve if the simultaneous conjugate match technique was applied. Again, we'll make sure that dB is selected to be able to compare it, and click on Apply, and then OK, then Simulate. So you can see that the basic gain of the transistor is much lower than the maximum gain that we can achieve with simultaneous conjugate match. You may recall how the simultaneous conjugate match is achieved. To remind you, we'll just open a graph, go on to New Graph, and this time it'll be a Smith chart. Let's call it Simultaneous Conjugate, and then we'll right-click on the chart, go on to Add a New Measurement, and then under Linear, we'll select GM1, and then Apply, GM2, then Apply, and click on OK, then Simulate. Now you can see that we've got two terminations shown on the Smith chart, and if the transistor sees GM1 at its input and GM2 at the output, then Gmax is achieved. But suppose that we don't want to achieve a gain of 11.4 dB, we want a lower gain, say 9 dB. Is there a way to adjust the match in such a way to increase the mismatch at one port or the other and hence decrease the gain? Yes, there is a way. In fact, you can either adjust the mismatch at the output or at the input. If you adjust the mismatch at the output, then you need to use operating power gain circles. If you adjust the mismatch at the input, you need to use available power gain circles. In this tutorial, we will be looking at how we can adjust the mismatch at the output to be able to achieve a gain which is different from Gmax. And the way this technique works is that we choose a specific termination for the output which we want to use to achieve our target gain, and then once we've selected this termination and we've put it at the output of the transistor, then we look at the new S11 of the transistor, the new input impedance of the transistor, and we conjugate match it in order for this gain to be achieved. So there are two steps here. You first have to select an output termination, but once you've done that, you have to conjugately match the input in order to achieve the gain that you've targeted using this technique. So let's open a new graph. It will be a Smith chart, and we'll call it Operating Gain Circles. And then the first thing we're going to do is right-click on the chart, go on to Add a New Measurement, and add GM2, the simultaneous conjugate match at the output, to this chart. Click on Apply, and then OK. This way we know where we started from. This is the termination that gives us the maximum gain, and we want to move away from it to achieve a different value of gain. Now, the way we can do this is by using operating gain circles. These are available in Microwave Office, so you don't need to calculate anything. We just right-click on the chart, go on to Add a New Measurement, and then under Linear and Circle, we will select GPC Max. This measurement allows us to plot circles on the chart which indicate what sort of terminations we need to use to achieve a specific gain. As you can see, there are two parameters that you have to set here. One is the step and one is the number of circles. So you're starting from your GMax, and then the simulator asks you what difference in gain there should be between each circle that's plotted. And let's say that we want to have a 1 dB gain difference between each circle, and we want to plot something like 4 circles. Click on Apply and then OK. Then simulate. Let's move the legend away a little bit. Now you can see that there are various circles on the chart. We said that we wanted 4, but the first circle effectively is a circle of 0 radius, which represents Gmax. That's our point P1 here. And you can see that it corresponds to a gain of 11.38 dB, which was indeed our Gmax. Then any point on the circle which is identified by P2 will indicate what terminations you must put at the output if you want a gain which is 1 dB less than Gmax, i.e. 10.38 dB. And the circle identified by P3 tells you what terminations you need to insert at the output in order to achieve a gain that is 2 dB less than Gmax, so 9.38. And obviously the one identified by P4 indicates the terminations that will give you a decrease in gain of 3 dB. So once you've selected the gain that you want and the respective circle, then you pick any termination on that circle and put it at the output of the transistor. Look at the new input impedance of the transistor, conjugately match it, and then you achieve the gain that's indicated by that circle. Now, if you're a bit confused, don't be. We will be going through this step by step and make sure that the process is clear. Now, suppose that we wanted to achieve a gain of 9 dB instead of 11.38. Well, we need to have a circle which gives us 9 dB in gain. Now, let's right-click on the graph, go on to Modify Measurement, and select the operating gain circles. Now, because we want 9 dB and our maximum gain is 11.38, 11.38 minus 9 is 2.38, so we'll just type 2.38 here. And as the number of circles, we'll have 2. Remember that the first circle is centered on the Gmax termination and it's got 0 radius, so you'll have to have at least 2. Then click on OK. And you can see that you didn't even have to resimulate. Now what you've got is the circle that you wanted, the circle which is relative to a gain of 9 dB. So first of all, we need to pick a termination on this circle. So let's press Ctrl M and insert a marker which allows us to see the value of the impedance on any point along the circle. Let's also change the marker readout by right-clicking on the graph, going on to Properties, and then the Markers tab, and choosing to denormalize the impedance to 50 ohms. Click on Apply and then OK. You can pick any terminations on this circle. You may wonder what termination you should use, considering that you have such a wide choice. There are other constraints when you design a transistor which may make one termination more suitable than another. For example, if you want to achieve a low pass response rather than a high pass response for your gain, or if you want to achieve a specific noise figure. However, these extra considerations are beyond the scope of our tutorial, and we'll be just choosing arbitrarily an impedance along the circle. So we can just click and hold on the marker and move it along until we get to a termination that we want to use. Let's pick one which has got a real value of 67.6 and an imaginary value of 33.3 approximately. So now what we have to do is devise an output matching network. So we can just go back to Circuit Schematics, open a new schematic, and we'll call it Output Match. Then, assuming that our actual load is 50 ohms, we want to transform our load impedance of 50 ohms into the impedance that we've just selected on the operating gain circle. So first of all, let's insert a resistor in the schematic to represent our load impedance of 50 ohms. Set its value to 50 ohms. Insert a ground by pressing Ctrl G. Then a measurement port by pressing Ctrl P, and then connect everything together. Now let's go back to operating gain circles Smith chart, right click on the chart, add a new measurement, and we want to be able to see the impedance that we are seeing for our output match schematic. So we'll go back to port parameters, select s-paramters and s11, and the data source name, of course, is output match. Click on apply and then OK, then simulate. At the moment our load impedance is 50 ohm and is right here, and we want to transform this into the impedance that we've selected on the operating gain circle. We've looked at matching networks extensively in other tutorials, so we won't be doing this in a great amount of detail. But if we want to match by using transmission lines, which is advisable at 6 GHz because the frequency is high enough for the wavelength to be low enough for this to be practical, we need to draw a constant gamma circle on the chart in order to carry out the match. As we know, we don't have a constant gamma circle measurement in AWR, but we have an equivalent which is constant VSWR circles. First of all, however, let's change the marker readout to magnitude and angle and reflection coefficient. Click on apply and then OK. The magnitude of our reflection coefficient is about 0.31, and from this we can calculate the VSWR. And the VSWR turns out to be roughly 1.9. So what we can do is right click, select add a new measurement, and then under circle we can select VSWR circle with a value of 1.9. Click on apply and then OK. Then simulate. And then you can see that we have a constant gamma circle which goes through the termination that we want to get to. To achieve the match we need to use a shunt open circuited stub, which will take us down to the constant gamma circle, and then a stretcher transmission line. First of all, let's change the appearance of the chart by going on to properties and then onto grid, and we will just display the admittance chart and take away the impedance chart and the values. Click on apply and OK. So now you can see even more clearly that what we need to do is move down this circle with an open circuited stub and then around the constant gamma circle to our final destination. So let's go back to our output match schematic, and we need to insert a couple of elements here. First of all, TLOC, which is the open circuited stub, and then TLIN, which represents a stretcher transmission line, and connect everything together. Then we'll set the initial values for both of these to 0, so effectively they are invisible to begin with, and then we'll double click on each element, make it tunable, and then select specific limits for the tuning. We'll go from 0 to 90 in increments of 1 for the stub, and then we'll go from 0 to 180 in increments of 1 for the transmission line. And also we must not forget to set the frequencies at which these electrical lengths are calculated to the right frequency, in our case 6000 MHz, which is 6 GHz. Now let's go back to operating gain circle Smith chart and click on simulate. The impedance that we see from the output match schematic is obviously still in the same place because we've set the electrical length of our stub and transmission line to 0. Now let's open the tuner, and then we'll start increasing the length of our stub, which is TL1, until we meet the constant gamma circle, and this happens for 33 degrees. And then let's increase the length of our transmission line until we get to the desired point. And this happens for our transmission line length of 103 degrees. So we've carried out our output match. We can close the tuner, and then we can go back to the output match schematic. So effectively what we've done is transformed the 50 ohm load into the impedance that we wanted our transistor to see at the output port. Now instead of copying and pasting this matching network, what we can do is just use a second port instead of our load. So we can remove our resistor, press Ctrl P and insert a second port, and then we can go back to our main schematic. We can make a little bit of space here, delete this connection, and then again click on the sub-circuit icon up in the menu here. And now you can see that as well as our transistor model, we have the output matching network. So we can select this, click on OK, and then place it here. So now effectively the output matching network has become a 2-port block, and it's quite easy to import it. So instead of copying and pasting our output matching network, we can just use this feature of the simulator to be able to just transfer it to another schematic. So now if we click on Simulate and we go back to our gains table, you can see that the S21 has increased, but only marginally. What we need to do now is conjugate match the input of the transistor to achieve the gain that we set out to achieve. So let's open a new graph and we'll call it input match. It'll be a Smith chart, of course. Then we right click, go on to add a new measurement, and then we need to go to port parameters, s-paramters and s11, and this will come from the operating gain match schematic, which is our main schematic where we've just put the output matching network. But what we want to display on this chart is not the S11 itself, but its complex conjugate, because we have to conjugate match the transistor in order to achieve the gain that we desire. So select conjugate, click on apply and then OK, and then simulate. Now this is the impedance that we want the transistor to see in order for the gain that we want to be achieved. So let's go back to circuit schematics, select new schematic, and we'll call it input match. Then, as usual, we'll start with the source impedance, which will be a 50 ohm resistor. Insert a ground reference by using Ctrl G, press Ctrl P to get a measurement port in, and then connect everything together. Then we can go back to the input match graph, and then right click, add a new measurement. It'll be S11, and in this case it'll just be its own complex value, not the complex conjugate. Remember not to make this mistake, and this will come from the input match schematic. Click on apply and then OK. Then simulate. In this case we're starting from a source impedance of 50 ohms and we want to transform this into the complex conjugate of the input impedance of the transistor, the input impedance of the transistor that we see after we've put the output matching network in place. So much in the same way as we did before, we need to draw a constant gamma circle on this Smith chart. In this case, however, we don't need to calculate the VSWR because we can directly measure it by using the Microwave Office VSWR measurement. So we can go back to our tabular graph and add a measurement here, and it'll be under the linear section, and then we'll pick VSWR, and it'll be from port 1, coming from the main schematic, which is operating gain match. Click on apply and then OK, then simulate. So you can see the VSWR seen at the input port is 4.42 approximately. So we can go back to our input match Smith chart, right click on the chart, go on to add a new measurement, and it'll be under linear, circle, VSWR circle, and the value will be 4.42. Click on apply and then OK. Then simulate. And then you can see that on our Smith chart we've got the constant gamma circle that we need for our match. Again, as we did before, we just right click on the chart, go on to properties and change the grid to just the admittance grid, because that's what we need since we will be carrying out a match with transmission lines yet again by using a shunt stub and a series transmission line. So we need to first add a shunt stub that takes us to the constant gamma circle, and then a section of transmission line that takes us to our final destination. So let's go back to the input match schematic and we'll do exactly the same as we did before. So we insert an open circuited stub and then a stretch of transmission line. We set both their initial values to 0, their frequencies to 6000 MHz, and then again we make them both tunable, and we select the range over which we want to tune them. We'll select a range of 90 degrees in increments of 1 for the open circuited stub, and then we'll select a range of 100 degrees for the transmission line in steps of 1. Click on OK, and then we can simulate and go back to the input match Smith chart. Again, you can see that nothing has changed because the electrical length values are set to 0. So we open the tuner, and then first of all we start increasing the length of the stub, TL1, until we get to the constant gamma circle, which happens for a length of 58 degrees. And then we start increasing the length of the transmission line until we get to a target point, which happens for a length of 28 degrees. So now we've also devised an input matching network to achieve complex conjugate match at the input. So let's close the tuner. Let's go back to our input match schematic, and remember that we usually flip this one to get a better graphical visualization of what's happening. So we just select your tool, right click, select flip, draw the axis about which we want the flip to happen. So this represents our source, and this represents the input of the transistor. Again, we can furnish this circuit with 2 ports, so we can again use the same technique with sub-circuits to transfer it to the main schematic. So we'll just remove the current terminations and then put port 1 right here, which is our source side, and then we'll put port 2 over here, which is the transistor input side. Then we can go back to our main schematic, which is the operating gain match schematic. We can make a little bit of space here and then remove this connection. Then we can click on the sub-circuit icon. Now we should have an extra one there, and we do indeed. It's the input match. Then we click on OK, and then we place it on the schematic like so, and then connect everything together. Now simulate, and now we can go back to our gains table, and you can see that the S21 that we see now for our main schematic is 8.99 dB, which is a close enough match to 9 dB. So we have achieved our design goal of having an amplifier which has got a 9 dB gain. You can also see that the VSWR at the input of the amplifier is very low, it's around 1. And this is a very good match, and it's a great thing to have. And it's not a surprise, of course, because we've conjugately matched the input of the transistor, and hence we would expect to have a low VSWR. But what happens to the VSWR at the output? Well, let's right click, add a new measurement, and then we go to linear and VSWR, and we choose the port to be port 2, click on apply, OK, and simulate. You can see, of course, that the VSWR at the output is not as good as the one at the input. And that is because we have actually mismatched the output to some extent to be able to decrease the gain of the transistor. If we chose a different termination on the same gain circle, we might have ended up with a different VSWR. So this might be an additional reason for choosing a termination over another. Now in this tutorial, what we've done is draw the operating gain circles, which give us the location of the terminations, which will allow us to have a specific value of gain. We can choose any point on the circle of interest, on the circle that gives us the gain that we desire, and then we can put the termination at the output of the transistor, or have a matching network so that the transistor sees that termination at the output. Then we measure the input impedance of the transistor, we conjugately match it, and hence we achieve the gain that we desired. In our next tutorial, we will do the exact opposite. So we will have circles that relate to the termination at the input. Once we pick the terminations at the input, we will then conjugately match the output to achieve the desired gain. And this other technique is called available power gain circles, and we will be looking at it in the next tutorial.